It's still ad hoc. We're trying to get our proposal funded, but we've been producing our products already. It's called the BC ARKSuperStorm because it's based on what happened with the ARK storm in California, and we're looking for the worst storm that had happened. What is this? We're going to develop a scale of extratropical cyclones, atmospheric rivers, that would focus right now in Western Canada. We're testing on the BC South Coast, and we're looking for partners. It was really triggered because people in Metro Vancouver and various areas wanted to know what is the third bullet, the worst storm expected. And so we're trying to focus for the future because we know we have so much warming. People want to know what to do. And we're the best forecasters in Canada, so we want to be sure that we're on top of it. We want to collaborate to make sure we've got what they want, and we want to help prevent harmful impacts. We're trying to set up an automatic advisory system to trigger emergency managers and start the discussion. Just for some vocabulary, ETC is extratropical cyclones. And most of you know what those are. Atmospheric rivers, I won't go in detail, but I throw everything in the same bucket. We have a way of detecting what is an atmospheric river, about 2,000 kilometers long. And there are lots of these detection algorithms, but several of us in the group have worked on that, and we'll show you what we get. This is a general schematic taken what Ralph et al. And their group in California have done. And we put a trowel, because in Canada we have trowels. Generally, this is defined atmospheric rivers ahead of the cold front. But for us in Canada, we realize it's almost impossible to tell where the trowel and the cold front end. We take it where the warm moist jet lifts off the surface. So this is a general idea of what we're looking for. It's very important for communications. Here is Christy Gordon used atmospheric river for this storm we're going to look at. January 31st to February 1st last winter. But you could see the stream coming in, and people want to know, well, how do you rate it? What is it going to do? What's our confidence? There's all sorts of issues, but argue as you may about this, it is a very useful communication tool. We can see in the total precipitable water here, it's about from November the 2nd, 30 to 50 millimeters of water coming into the coast. But what will actually happen? Like this gives you a heads up, but it isn't going to rate the storm. You can track them. They're started initially with integrated vapor in the vertical. Whipping Mo of our lab has put this together. This shows for that same storm coming, a moisture stream coming up, and we can rate it quite high for integrated vapor. But then what's most important is it coming our way, or is it just sitting there? So this is the transport, the lower one, integrated vapor transport. That is what we're going to use throughout this talk, IVT. And in this case, you see it went up almost to 1,200. There's a scale Ralph Group has adopted, and we've been testing it. It works quite well for our region, and I'm going to show you the results. It goes from 0 to 3 days, and out from 0 to here is about 1,500 kilograms per meter per second. That's for IVT. So if you integrate IVT with time, say over 1 day, 2 days, 3 days, you get kilograms per meter are these the units. Not to drive you nuts, but this is how we rate it. AR1 is beneficial, AR5 is hazardous. What people are asking us is, what do we expect in the future? How well can you forecast it? So we're going to look through. Rita So is a smart gal who's working with us, and she's now the manager of this project of ARKSuperStorm. She's put together this paintball plot, and so that every location has the storm rated based on the global model here. I popped up Sumas for you. That's on the border just north of Blaine and in the Lower Fraser. And here we could come up with, identify that for this IVT, it would be an extreme storm, about a category 4. Now we have a classification scale, and this, we're still discussing on it. It has many different aspects. On the left is a category, then we use IVT, but it depends on the duration of the storm. And the return period of the event we're looking at, be it heavy precipitation, heavy freezing rain, heavy snow, floods, goes from out to 200 years would be a category superstorm. I looked over at the Ottawa storm, and it IVT categorized. That was for all the tornadoes they had there recently. The outbreak of 80 tornadoes or so came into a category 4 or 5. So there's possible promise for other things. Also, winds is sometimes that have the stronger ones, we get high winds. So we're going to have a number of ways to rate this, but this is what we're developing. The ARKSuperStorm is the worst expected. It might be the category 5, it might be 5 category 2s, but this is part of our consultation. Why model it? Well, we have to be prepared for it. And why categorize it? Because I like to categorize everything, but we categorize earthquakes, hurricanes, tornadoes, everything, and we're not categorizing our mid-latitude cyclone. I would like one named after me too, but anyway, so everyone does. But anyway, just be on the anyway, go on that ARKSuperStorm category 5 are like the major impacts may not be mitigable. We might not be able to resolve them. They're catastrophic unless you're prepared. And we're moving in Meteorological Service of Canada and around the world towards a impact-based risk communication. This is to start the communication, and we have to work with people. And we have a rapidly warming world. We want to know what's going to happen. So the next here, we're going to talk about this storm from last winter. This shows the moisture stream coming up, and you can see several cyclones along it. The pictures on the right are what our forecasters in Vancouver produce these amazing plots on our Niño system, and then we send it to Avalanche Canada, who share it. And now everyone loves to see them because they're really, really great. But because we can't translate it in French, we can't share them, but hopefully we can share them in the future. This is the radio sonde. We have other profilers which show this, but you can see this is at Port Hardy, Northern Vancouver Island, that it's a very strong southwesterly flow all the way up to the tropopause, and it's very moist. In this case, we had about 140 millimeters at Hope, so that is 3 times the precipitable water, and we had rates of 5 to 40 millimeters an hour. We had washouts at Sasquatch ski area. There was the road washout. They were closed for 3 days. They had to helicopter people out. Effingham on the west coast had incredible precipitation. Here I'll show you Effingham. We love that station. It's a forestry station, and we've had them check it all the time, but it really has a lot of rain. 400 millimeters in 2 days. This is the Canadian precipitation analysis, which takes all the best data you have and then throws out what it doesn't like and then uses model to fill in. It's not always right, but it is pretty amazing in many ways. But realize it's model infill. Still, it got that in, very close to the actual precipitation for Effingham, 250 millimeters in a day. How do we rate that? Then we're looking for return periods for precipitation. We're looking at 1 hour, 1 day, 2 days, 3 days, storm, month, anything we can to get an idea of precipitation rate, intensity, antecedent precipitation, preconditioning. But realize these records for Pitt Meadows is in the Lower Fraser, so is Agassiz. They're only about 30 to 50 years. We're not like Europe. We don't have really, really long records, a few 100 years, but it's pretty hard to get a 100-year return period or 1,000 years for the 1 in K event from data that short. This is from the River Forecast Center. It showed just quickly on the top is the snowpack depth, how when the storm came through, boom, the snowpack not only had risen, but then suddenly dropped because it's a rain on snow event. So we have these compounding issues typically affecting us in winter, and they're essential to catch in this. Lower, it shows the return period for the river discharges. We'll zoom in on the lower one. We can see that we had between 5 and 100-year return periods. So it would categorize around a category 4 storm, but some areas just a 1 to 2. So that's why we're going for this paintball approach, because that's what return periods are. Unfortunately, there was lots of flooding on Vancouver Island. 4 people died, and it was a lot of damage. It was a major storm. How did our rating occur? Well, on the upper left is Rupert Moa set up this integrated vapor transport. Sorry, the colors aren't consistent, but it's to pull out the features a little better. The middle plot is duration, and the right is maximum AR. Rita So has done up this plot for us. Now, upper right is what the global shows. You could see that it did nip southwestern Vancouver Island near Souk with the category 4, but the other places were not category 4. The lower is analysis data, which showed it a little bit heavier. So there's consistency. This is the interface we want to show them, combined with the paintball plot, and we'd like it to go out several weeks. Now, what will happen with warminess for these storms? We look at a lot of areas along the coast. Alex Cannon has taken out IVT, which is total integrated throughout the whole area of the domain on the right. This is for the Canadian model, but what warming scenario should we use? Well, he decided the best would be 3.2 by 2100, but it could be as much as +6 if we keep burning coal and don't do mitigation. It's very unlikely to be less than 2. So 3.2 is what we went with, warming. Okay, this is to show you how to use these plots. So what he did is he categorized all the, he had 7,000 model realizations from the year 1950 to the year 2100, using this classification. Let's give it a run. How does it work? It's on the west coast of Vancouver Island. Here goes the duration, 0 to 10 days. So there you can see we have increased storminess and increased category 5 storms coming up. Now, if we on the right, it's a whole bunch of examples of the plots. You can see most of them show about the same. On the left is the Japanese reanalysis, which many of you have used. And there it shows that we've had a few category 4 storms, or maybe one category 5 storm, but they're rare, but they do happen. Now, what will happen in the Arctic? He just gave me this hot off the presses. This is way up north, northern Canada, northwestern. It starts to look like my bubble bath when my son was young with the cat that jumped in as you get to 2100. There are many category 5 storms, and they've never been there before. So they're lasting 10 days at Tuck. And we've run a whole bunch of models. They show about the same thing. On the left is the Japanese reanalysis. We haven't seen that before. So for +3 degrees, we're going to have many more category 4 to 5 storms, and 5 is catastrophic. Now, we don't know for sure what that's going to happen, and it's going to change with time, but it's a big impact, obviously, because of the ice and storm surges and waves, and every area has a different impact. And he did this plot for us. This suggests on the left is annual maximum IVT, and the right is the storminess, or the horizontal axis is time. On the right, I'm showing you that from 1950 to 2100, taking the average percentile of the maximum atmospheric river, storm flux, whatever you want to call it, it will increase 5 times. This is with 6 degrees of global warming.
Mindy, you have about 2 minutes left.
Okay, we're just about done here. And this is for Vancouver. Here we can see that on the left is the same plot. And on the right, you can see that you could do from 0 to 6 degrees of global warming. And here we take 3 degrees. It's what you're going to have is a 20-year event becomes a 4-year event. You can choose your type of warming. So what we can expect by 2050 is a very much stormier due to global warming. Conclusions is we want to rate these storms. It's very valuable to managers. There's a predicted increase in intensity and magnitude that would threaten infrastructure. In short, we'll have to spend billions of dollars to upgrade everything. The storm classification is adapted from Ralph and works quite well in Canada, but the ARKSuperStorm is to get the 1 in 1,000-year storm. Obviously, that's just to sound like Noah's Ark, and it's to be the worst storm expected. So that's why I call it ARKSuperStorm, because we want what's the worst expected. And then the last one is we were trying to get it classified and We want to further classify by return periods, preconditioning, and regional sensitivities. And thank you very much.